Okay, I think we're online. Hello, everyone. Welcome to the afternoon session on the topic of segmentation and matching. My name is Marc. I'm a senior researcher in the computer vision and geometry lab at ETH Zurich. Before I started, quickly wanted to refer to the Discord channel for this session. So please use that to post your questions at any time. After the talks, after each talk, we will read and discuss them. Now I'm very much delighted to announce an invited talk by Laura Leal-Taixe. The title of her talk is In Defense of One-Shot Fine-Tuning of Video Object Segmentation. As a short introduction, Laura is a tenure-track assistant professor at TU Munich. She's doing research in the area of computer vision and machine learning. Laura received her PhD from Leibniz University in Hanover in Germany. During her PhD, she also spent a year as a visiting scholar at the University of Michigan Ann Arbor in the US with Silvio Savarese. And she also did her master thesis in the US at the Northeastern University of Boston, while she was studying at Technical University of Catalonia. After her PhD, she spent 2 years as a postdoc in photogrammetry and remote sensing group of ETH Zurich. Among many other awards, she's a recipient of the prestigious Sofia Kolorskaya Award that she got in 2017. Her research has been focused on multiple people tracking, object detection, and pose estimation. And she was the driving force and regular organizer of the multi-object tracking challenges and the corresponding benchmark. Now with her research group growing, her interest has broadened a lot, and we have seen great contributions of methods for better understanding dynamic scenes, in particular in the area of segmentation, generative image, and video modeling, depth estimation, video supervision, and many more. Laura, we're really happy to have you here, and we're looking forward for your talk.
Thank you, Martin. Thank you for the introduction. Welcome, everyone. I'm really happy to be here and give this talk. So today I'm going to talk about video object segmentation. And in particular, I want to revisit an idea that we presented back in 2017 about one-shot fine-tuning for semi-supervised video object segmentation. So first, let me introduce the task. In video object segmentation, we want to generate accurate and temporally consistent pixel mass for objects in a video sequence. So you can see here some of the ground truth annotations for the Davis sequences, single object, multiple object, and you can see already the challenges that video object segmentation poses for computer vision researchers. So first of all, we have usually a moving camera, moving objects, and therefore there are very strong viewpoint and appearance changes. So it's really hard to make assumptions about consistent appearance or constant motion. We also have frequent occlusions, for example, here in the bus sequence where the bus is occluded by the tree. And you can see also the level of detail of the annotations in this Davis benchmark, where we have parts of the bus already segmented. And this is the kind of output that we're expecting to get from computer vision algorithms. And we have also, for example, shape changes or scale changes that actually don't allow us to make the assumptions that we would do in other tasks in computer vision. So for video object segmentation, there are two trends, roughly, so at a very high level. One is to leverage appearance, so try to learn the appearance of the object to segment, and then try to adapt it through the video sequence. And the other one is leveraging motion. So we can make some assumptions about the motion of the objects in our scene, and therefore we can use that to follow the objects, for example, using optical flow priors. The thing is that each of these methods has its pros and cons. And for example, we can see that when you leverage appearance, you are definitely more robust to occlusions because you have a model of how the object should look like after the occlusion, while leveraging motion is not so easy when you have a long occlusion and you have to predict where the object will reappear and what kind of motion has it gone through behind the occlusion. And of course, the opposite. If you're leveraging motion, it's easier to deal with strong appearance changes, scale changes, illumination, and shape changes. So each of them has its pros and cons. So in this talk, I want to focus on a particular subtask of video object segmentation, which is called semi-supervised video object segmentation, because we are given the first frame ground truth of the object that we have to segment. And our task is to segment the object in all other frames in the video. And you can see, for example, this sequence, which is challenging because we have an occlusion here in the middle where the object has completely disappeared from the scene and then reappears later on in a slightly different position. So I want to start by presenting a work that we did back in 2017 called OSVOS for one-shot video object segmentation. So in there, we wanted to learn the appearance of the object. So we forget about the motion for a second, and we focus on making a really strong model of the appearance of the object to track. And since we're dealing with semi-supervised video object segmentation, we know that we have the ground truth first frame mask. And therefore, what we propose to do in that GCPR paper is to do a series of fine-tuning steps, fine-tuning of a neural network as a means to learn the object's appearance. So we're going to fine-tune the entire network on just this one first frame mask of the object. So the whole idea is to separate the training of the network for our purposes. So we start with the first training, which is pre-training on ImageNet, like we do for any network in computer vision. And this gives us the edges and basic image features that we need to further process this image. In a second step, we need to tell the network what kind of task are we trying to solve. So in this case, we need to teach the network how to do video segmentation. So we take the entire Davis training set and we train what we call the parent network. Now, this parent network is going to learn in general what it is to do video object segmentation. But of course, it doesn't know exactly which object it has to segment. So this is why we have the third step, what we call the fine-tuning step. And the idea there is that we take the first frame of the test sequence, this ground truth mask that we are given, and now we fine-tune on that first frame. So essentially, with this third step, the network can learn which object it has to segment. So it goes from general video object segmentation at step 2 to this object segmentation for step 3. And of course, we need to do a fine-tuning step for each different object that we want to segment. Now, technically, this fine-tuning step, what it's actually doing is it's overfitting slightly to the test sequence first frame. So of course, we're fine-tuning only on this one first frame. So technically, the network is overfitting to that frame. But in this case, overfitting is good for us because it's learning the appearance of the foreground object and also the background object. Now, at test time, very easy. We just take each frame and we process it independently. So no need to compute optical flow or to compute any kind of temporal information. So with this paper, what we did is we fully exploited the data-driven trend in the community. So we thought, well, if you're given a first frame ground truth, you're given this piece of data, even if this data is not really large, it's just one frame, we can still use it to train on it. And in our case, we first train on all the other sequence of the Davis dataset. This is our parent network. And then we fine-tune on this frame. Now, here what I'm plotting is the results that we get as we further and further fine-tune. So of course, you can start with a parent network, which in a really fast time, 102 milliseconds, it will give you a result. Now on the y-axis, we have the region similarity, which is the accuracy for segmentation networks. So you see that the accuracy is roughly on par with the state of the art at the time. But as soon as we add this fine-tuning step and we know which object we have to segment, of course, the results start climbing up. And the more time you spend on fine-tuning, the more your results improve. Now, at the time, we had quite a boost of almost 12 percentage points with respect to the state of the art at the time, which was an optical flow-based method. Now, the good thing about this method is, as I said, it recovers from occlusion. So if we start with this first mask and we have this case in which the biker goes behind the tree, we have the first occlusion, we see that the method can nicely recover while optical flow-based methods will get stuck in this tree. And the same happens for heavier occlusions where we see that there is a huge error here, which would be carried to the rest of the frames with optical flow, while in our frame-based method, this can be completely, of course, erased, and we can start new with a new frame and obtain a good mask. It can also nicely handle dynamic scenes, although as I will show by the end of the talk, we can do a little bit better on the bottom right scene. Now, cons about this method. We see that if we fine tune on a first frame that looks like this is the mask that we're given as ground truth, we see that, for example, some of the objects behind the breakdancer cannot be seen in this first frame. So when the network overfeeds to this first frame, then you apply it on subsequent frames, what you get is a result also on this person that was occluded. And this is because the network never learned that this was actually a background object. At the same time, if parts of the object, of the foreground object, are not seen in the first frame, in this case, the breakdancer is turning, and therefore this part of the back of the legs was never observed, it can be that it's not recovered as a foreground mask, but as a background one. Because there is actually no notion of object. We predict pixels individually, which means that we will not have this notion of a shape or an object, in this case, how a person should look like. So these are two disadvantages that we want to try to solve in this case. So in order to solve these disadvantages and some others that OSVOS had, many methods started to build on top of OSVOS. So we have a series of methods, the OSVOS family, how we call it. So in this case, I'm going to plot the methods. The more to the right they are, the faster they are, the more to the top they are, the better they are in terms of accuracy. So for example, we can see ONAVOS, also published in 2017, in which the appearance is adapted by fine-tuning at every frame. We can see OSVOS S, which adds proposal to add this notion of object that we were talking about. Or we can see PremVOS, which includes proposals, optical flow, and a bunch of other tricks to achieve a really, really high accuracy, even though the method is really slow. But eventually what happened is that this fine-tuning concept, the idea of fine-tuning on the first frame, was kind of forgotten, and people started moving to other concepts that were faster and deliver better results. And in this talk, I want to convince you that this is just because of a few key design choices of OSVOS that we can actually overcome. So first of all, there is a high test run time for OSVOS. We need to fine-tune for around 1,000 epochs per object. And second, the learning rate that we use for fine-tuning and obtaining these results is quite handcrafted. So it doesn't always generalize to new scenes. So in defense of one-shot fine-tuning, we have identified 3 design choices that have currently prevented this fine-tuning to be efficient and to obtain state-of-the-art results. The first one is that in this separation of the training, where you first train the parent network and then do the fine-tuning later, the parent network optimization doesn't happen so that the subsequent fine-tuning achieves the best results, right? So these 2 steps, step 2 and step 3, are completely separate. So the parent network is not optimized for the subsequent fine-tuning. And the 2 other problems we already saw, the excessively handcrafted hyperparameters, we would also like to get rid of those, and the fact that the network does not really know about objects, even though everything that we have to segment are objects that probably we have in other datasets in computer vision. So the work that I want to present today is eOSVOS, short for efficient OSVOS. And the idea here is to change these key design choices in order to achieve a method that is much faster and is also much better, achieving almost state-of-the-art results. So we're going to look at these three problems separately, and we're going to try to solve these problems with three different concepts that are commonly used in computer vision. So we'll start with problem 3. For the problem that the network does not leverage the concept of objects, we know that we have models that do leverage objects as a concept, that do know about objects and object masks. And therefore, the only thing that we need to do is we need to choose the right model. In this case, we choose MaskRCNN. And the advantage of MaskRCNN is that it first performs object detection and then performs object segmentation, which means that the segmentation is in a very defined narrow space. We're not looking at the whole image for the background object, but we know roughly what it is. So we don't have heavy foreground background pixel imbalance. And also it's easier to discriminate between multiple objects that are going to be found in that image. Now, the interesting part are the other two problems. So for the other problems, what we propose to do is we propose to resort to meta-learning. We want to meta-learn the model initialization, that is the parent network training, and we want to meta-learn the learning rates so that we don't have to do a handcrafted hyperparameter search. So we propose to replace the transfer learning concept with the meta-learning concept. And in this case, our idea is to take the second step of training of OSVOS and the third step and meta-learn those. So learn the model initialization that would be equal to the parent network training, and also learn the learning rates that are going to be used for the subsequent fine-tuning. And you can see here an example taken from the ICML 2007 paper in which they show this concept of meta-learning, in which you start with a series of parameters theta, and then for each of the tasks that you want to target, you can evolve these parameters to theta 1, theta 2, or theta 3, depending on the task that you have at hand. And this is exactly what we want to do. We want to find the initialization, which would be the theta parameters, and we want to perform different fine-tunings for each of the sequences that we have to test on. So the most important thing when we are dealing with meta-learning is defining the meta task. So defining suitable tasks so that meta-learning can actually learn what we want and not have problems like, for example, memorization, which is something that I will talk about in the next slide. So in our case, the meta tasks that we have for VOS are the task of fine-tuning. So each of the tasks that we will create represents one fine-tuning optimization, one sequence. Now, the training of the meta task corresponds to the first frame image and the first frame ground truth mask. This is, for example, for one sequence, we have this image, and the red mask is the object that we provide as ground truth mask. And as the test set for the meta task, we have all subsequent frames. And this nicely shows the task that we have when we're actually dealing with OSVOS, right? The task of training on one single image on the first ground truth mask, and then testing on all the other images. And what we want to do is to, as best as we can, training on this and testing on all subsequent images. Now, another important thing that we need to take care of when we're dealing with video object segmentation and meta-learning is the memorization problem. So this has been well studied in image classification, and there it's shown that the network can potentially memorize the outputs. So instead of learning the task at hand, the network finds it easier to just memorize the output of the test of the meta tasks. So in order to counteract this, what they do in image classification is they randomly shuffle the labels of the objects that they have to classify. So that, dog is not always one, but the labels are shuffled. And this is something that we could also do here, shuffle foreground from background. But we actually have a better way, something that empirically works better, and it also leverages the nature of the multiple object sequences. So in our case, we do have multi-object sequences. And for this, let's imagine we have a sequence, we have 3 objects, and we will create 3 meta tasks for these 3 objects. And each of the objects will be foreground in one meta task, while the other 2 are going to be background. So essentially what's going to happen is that the network will receive the same input image, but will be forced to learn different outputs. Because in one meta task, the output that is going to be learned, or that you have to output in order to get a good loss, is going to be object 1. And in the second task is going to be object 2. So like this, what we're forcing the network to do is we're forcing it to look at the first frame ground truth and to really output something that is based on this first frame ground truth and not just something that the network has memorized. So in this case, we force the network to perform this fine-tuning step, to look at the training of the meta task, which is this first frame ground truth mask, to learn the appearance from that, and then make a prediction in all the other frames. So let's talk about the optimization now. So the normal OSMOS optimization, and in any setting, supervised optimization of networks, has such a shape in which you have theta f, which would be our network parameters of our model f, and we have g, which is our optimizer. This optimizer can be SGD, ADAM, or whatever optimizer you want for your network. And the goal is to obtain the best set of network parameters given the optimizer. Now in meta-learning, it's slightly different. And what we have there are essentially 2 optimizations, one in the inner loop and one in the outer loop. So let's look at the one in the inner loop. In the inner loop, what we have is the classic fine-tuning on the first frame ground truth. This is what we have been doing for OSPOS. We take our training set, this first frame ground truth image, and we optimize the parameters of our network given our optimizer. The thing is that these are just the constraints for an outer loop, because what we really want is we want that my test accuracy increases. So it's not about fine-tuning on the first frame for the sake of fine-tuning, but we actually fine-tune and we output a model, parameters theta f with optimizer g, that are going to be then used to see how this model performs with the test images, which are all the other images in the sequence. So remember that dtrain is the first frame ground truth, while dtest are all the other frames of the sequence where you have to try your fine-tuned model. And this is exactly the idea, right? We don't fine-tune just for the sake of fine-tuning and stop at 1000 epochs, but we fine-tune, we look at how it performs in the test set, and then we make a decision that I will talk about now. So this inner loop, outer loop play is perfectly suited for our task of performing fine-tuning, but not for the sake of fine-tuning, but for actually optimizing something on the test set, which is a completely different set. So basically what we want is we want to train eOSMOS on the training task set, again, this first frame ground truth, such that this fine-tuning on any given first frame yields optimal results on the corresponding test set, which are all the other frames of the sequence. Now, another interesting concept here is what are we optimizing in the outer loop? So in the inner loop, as we said, we fine-tune the model for n epochs, in our case, 5 or 10, given a fixed optimizer, given a fixed G, which corresponds to an initialization and a learning rate. So in the inner loop, G is fixed. In the outer loop, what we're trying to do is we're trying to optimize G. And in this case, the parameters of the optimizer that we want to change, that we want to optimize, are the learning rates and the model initialization. The model initialization corresponds to the parent network training of OSVOS, while the learning rates corresponds to the learning rates used in the fine-tuning step. So these are the characteristics of our optimizer that we want to optimize in the outer loop. So again, we're going to do one outer loop optimization, but multiple inner loop iterations, right? So the inner loop is going to give us models with a certain optimizer, and the outer loop is going to test those models and tell the inner loop how to change the initialization, how to change the learning rates to try to optimize the output on the test set. So let's see a little bit of results to see what is the actual effect of all these meta-learning. So we're trying 3 different sequences, the 2 Davis sequences, single object and multiple object, and also the YouTube VOS. But today I'm going to focus on the ablation studies because these are the interesting ones that actually show us how the method really works. So of course, the first thing that we need to do is we need to make a comparison with OSVOS by taking our new model, which is Mascar CNN, and performing the OSVOS type of training. So parent network training plus a single learning rate that we search manually by grid search, and seeing what is the accuracy of that model. So in here, what we can conclude is that we definitely need a lot of epochs to reach a nice accuracy. So it's no wonder that OSVOS also needed 1,000 epochs to actually reach a nice accuracy. So we turn now to the meta-learning part. So in the first row, we can see what happens when we add meta-learning for model initialization and single learning rate optimization. So again, the model initialization is like the parent network training, but in this case, we have only one single learning rate, which we don't choose by grid search, but we choose by using the meta-learning optimization. And we can see that even with this, we can have a boost of over 30 points in accuracy with respect to the same model fine-tuned for 10 epochs. And even with the manual model trained for 1,000 epochs, we're still much, much better. So we can see here the power of meta-learning. Now in the second row, we have some neuron level learning rates. So now we're not going to have a single learning rate for the whole network, but we're going to have neuron-specific learning rates. And this is something that we can still do, and it still gives us a nice boost in performance. So in the paper, we also provide a couple of test time improvements, and these are mostly based on other papers. So the first one is based on our paper Tracking Without Bells and Whistles, in which we use it for multiple object tracking. And the idea there is to perform bounding box propagation. So the idea is that we do it for faster CNN in the ICCV paper, and we do it for Mascar CNN in the EOSVOS paper. But the idea is that you can use the output bounding box location at frame T as a proposal for frame T+1. And like this, what you do is you impose certain constraints on how the object can move. So we assume that the object moves smoothly in space. So we add some sort of temporal coherence to OSVOS. And this gives us also a nice boost in performance. And it's something that can be directly applied at test time and doesn't change at all what we do in the meta-learning phase. The second one is online adaptation, like the ONAVOS paper, BMVC 2017. And it's the idea of online adaptation, the idea that an object moves, new parts of the object are uncovered, and we need to adapt our appearance model. So in our case, we can also do this at test time and adapt the appearance every 5 frames. Now, the cool thing about this is that there are no changes that need to be done in the meta-learning phase. So we train our meta-learning without any knowledge that online adaptation is going to happen. And then we can simply turn on online adaptation at test time, and the meta-optimization is still going to work. And this is because the concept is still the same. The concept of taking an image, taking a mask, and training for as long as needed, as long as the meta-learning decides, and with the learning rate that it decides, and with initialization that it decides, in order to get the best results possible in all the other frames of the sequence. So this concept is something that fits very well to the online adaptation. So this is our final model when we fine-tune for more epochs, 50 epochs or 100 epochs, reaching really nice results. And here again, the meta-learning has not been changed at all. We train it for 10 fine-tuning epochs, and it nicely generalizes to more fine-tuning epochs. So here we can see a sequence, some qualitative results where we have this scar sequence, which worked actually quite well on OSVOS with a Jacquard index of 83.5. And we further improve it with our model. And you see that the main changes are that the mask that you obtain in the output is much more coherent with the shape of the object. So you see the mask on the left of OSVOS has some holes, and the mask on the right is much more coherent and respects this idea that there is a car in there, there is an object as a whole. Of course, there are some challenging cases, especially when we move to multiple objects. So in this case, we have the surfer, we have multiple objects because one object is the surfer, the other are these strings, and the third one is the board. So what can happen is that at some point with very thin objects, for example, Mascar CNN doesn't like thin objects so much. And what ends up happening at frame 40 is that the proposal box in which Mascar CNN is trying to work on does not really contain the object, in this case, the board. And therefore, we have a failure case. So of course, using Mascar CNN as a prior to locate the object and then segment only in that region is something very powerful, but it also has its disadvantages like we show in this case. Here we have a challenging case in which we actually do have a good output, and we can separate the person, the gun, and also this kind of stick that the person is holding. And even if the viewpoint changes a lot, we can still get nice proposals and nice segmentations out of them. And one of the most challenging cases is when we have large objects occluding the objects that we're segmenting. Like in this case where we have these 3 persons walking, but then suddenly the blue person disappears. And at the same time, the red person becomes quite occluded. In this case, the bounding box propagation plus the fact that we are using proposals means that we will get 2 persons confused and put in one. And we will get this displacement of the person with the red mask towards this big person here. So of course, these are very challenging cases and something that we're looking for towards working in the future. So as a conclusion, I've presented this concept of fine-tuning on the first frame ground truth mask. This is a very powerful way to learn objects' appearance, and it nicely follows the trend in the community of performing data-driven operations and solving tasks in a data-driven way. And we show that this has a lot of potential if we change a few key design choices. In particular, for the task of first performing parent training and doing subsequent fine-tuning, we can use meta-learning to really make the network learn what we want it to learn, which is training a parent network, which is not good or doesn't deliver good results for, alone as a standalone object, but it's actually a pre-training of a subsequent fine-tuning. So this idea that the parent network training has a subsequent fine-tuning is something that we can show the network how to do with our meta-learning optimization. So hopefully this will inspire people to reconsider fine-tuning for video object segmentation and continue the work that we will present this year at NeurIPS 2020. So with this, I would like to conclude my talk. Thank my PhD student team who did the work for eOSVOS. And if you have any questions, I will be happy to answer them.
Okay, Laura, thank you very much for this very interesting talk. Very nice results. I would like to point again to the Discord channel. Please post any questions there for Laura. We have a few seconds delay between the live stream. So I would start with some questions myself. The first question would be, it seems like it's very important, since you're kind of starting with the first frame as to identify the object and then essentially propagate the appearance information. Like, how important is it that the appearance actually has similar statistics, right, for the occluded part in the first frame? For example, for the car that you see there, it is actually the case that it's a very similar appearance statistics on the other side when it's turning around. But if this is not given, like, how important is this? Like, did you do some experiments in this regard, or is there some part of the data set that is more difficult in this respect?
Yeah, so actually this is an excellent question, because this is really the point that we want to tackle here, right? So there are some sequences in which the object basically doesn't move at all, right? And then you have, the camera is moving a little bit, but the object is mainly in the center and you're just following. So for this, of course, this fine-tuning concept is perfect. You just can heavily overfit, and then you just apply the model and you segment the thing perfectly. Another question is if your object is similar, like for example, the car, but not exactly the same, or even a person, right? That front and back of the person is not really exactly the same. So there we can see some sequences, like there's, for example, one with the dancing girl. I don't have it here, but when she turns around, usually OSVOS loses part of the back because it has a different appearance, right? And the idea there is that you should not fine-tune so much on the appearance of the dancer for that sequence, right? So ideally what you would like to do is you would like to fine-tune more for the sequences where you foresee there's not going to be a lot of motion, and fine-tune less for the sequences where you see there's going to be more motion. So that is something that we're also working in the future. But otherwise, the only thing that we can do is perform the online adaptation, like we show here. So here you can see that there's quite a nice boost in results when we perform online adaptation. These are these two results. So you can see almost like 4 points in boost. And if we look at the sequences that are being improved with the online adaptation, these are the sequences where, of course, there are more changes in the appearance, right? So with the online adaptation, you have a chance to look at how the object changes, but slowly, and adapt the appearance quickly for the subsequent frames. I don't have results of like specific sequences where it completely fails, but this is definitely a very, very important issue and a very important question.
Yeah, thank you. That was a very elaborate answer. Maybe to follow up, this meta-learning concept basically replaced the original parent network training, but the optimization seems a bit more sophisticated, and especially something like learning rates is something that is quite important also to choose. And I'm wondering like how stable it is to learn this approach. Is this very sensitive, or is this something that wasn't really a problem if you have these essentially iterative optimization with this inner loop and outer loop?
So definitely it looks more complicated than it is. So of course, one nice thing is that the optimization will choose the learning rate of the fine tuning for you, right? So parent network training and fine tuning comes together in the form of initialization plus learning rate, or let's say it provides you with the learning rates for the fine tuning, right? So you don't need to worry about the OSVOS type of training. Of course, your meta optimizer is going to have a learning rate of its own, right? I mean, this is just an optimizer that optimizes an optimizer. So what we observed is that the learning rate of the meta optimizer is much less sensitive, so much more robust than the learning rate of OSVOS, which is essentially what we want, right? If we're solving then a more complex problem and it's much harder to get a solution there, we will not be solving anything. But it is much more stable to play around with the meta optimizer learning rates than to play around with the OSVOS learning rates.
There is a related question from the Discord. How prone is the meta optimizer to local minima then?
Well, depends what you mean by local minima, right?
That's a good question.
So I mean, of course, we're always going to end up in a local minima, right? In deep learning, that I'm not discovering anything here.
It's like undesired local minima, right? That you basically don't have nice results anymore.
Okay. Actually, it's very important for that to define a proper meta task, right? So the problem of memorization is a huge problem. And as soon as we started introducing multiple object sequences and we started playing around with this idea that for a given image, the network cannot memorize results, then things become more stable, right? Then we have other tricks, like for example, here you see that we use group normalization, we change the loss function so that it nicely reflects the problem that we have at hand compared to the OSVOS loss function. But these are small changes. So overall, if you choose your meta task correctly, you're bound to get a nice result. And it's not as difficult as it might sound with all this inner loop, outer loop optimization.
I might have missed it in the talk, but maybe like what is the key component, key ingredient to actually get such a significant speed up over the previous method?
Well, the idea is that, first of all, you're choosing the learning rate, right? So you can potentially be more aggressive with the learning rate. The meta optimizer can choose to be more aggressive. And so what happens is that you see here, if we choose the learning rate by just learning rate search and we try to make a nice surge of really harsh learning rates, really slow ones, we see that with 10 fine-tuning efforts, it's not so easy to get nice results, right? So you need to spend a lot of time in fine-tuning. While in our case, we just spend 10 fine-tuning epochs, right? So we have also versions that are a bit slower. We spend 100 fine-tuning epochs, and this delivers better results. But already with 10, we have quite nice results. And of course, this is what you need to do at test time, right? These are the fine-tuning epochs that you get the image at test time, you fine-tune on it, and then you segment on the video. So the faster you can do this fine-tuning, the better.
Okay, very good. So there are no more questions from the chat. I have a lot more questions, but we're running out of time. Maybe a very last question, looking a bit into like maybe future work. You know, I'm a 3D guy, and I always have the feeling that like 3D information might actually help in these tasks, actually to track the object. What is your opinion? Like, is this something that should be modeled explicitly, or is this fine to kind of be intrinsically learned by masked RCNN by learning shape and appearance models?
Well, I mean, you have both paths, right? Yes. The problem I think between 2D and 3D people is that there are no data sets that tackle common problems, right? So if we would have, for example, a Davis data set with multiple cameras where all the annotations are matched between the multi-views, then maybe someone would do something in 3D, right? Mm-hmm. So of course, it is much easier to reason about occlusions in 3D it is much easier to obtain not only a model of the appearance, but a model of the shape in 3D. So these are, of course, things that would boost results immensely, right? The question is then, what happens if you have then just one image and you want to perform segmentation on one image, right? The question is, how can you transfer all this knowledge into a network that then works on the monocular case? I think this is an interesting research question.
Okay, thank you very much. I think we have to move on. Thanks a lot for this very nice talk. Very great results and deep insights. We continue with the next talk. This is joint work by Tim Rolff, Marc Rautenhaus, Stephan Olbrich, and Simone Frintrop. The title of the talk is Segmenting Computer-Tomographic Scans of Ancient Clay Artifacts for Visual Analysis of Cuneiform Inscriptions. And the talk is given by Tim Rolff. Tim, please go ahead. The floor is yours.
Thanks for introducing me. So our talk is on the, as you mentioned, on the segmentation of computer-tomographic scans of ancient clay artifacts, and for basically the visual analysis of cuneiform inscriptions. This is part of the Excellence Cluster Understanding Written Artifacts, and this cluster is mainly located within the humanities, and it studies how historical written artifacts such as manuscripts or inscriptions have actually shaped human culture. So before I want to dive right into our topic, I want to briefly introduce what these artifacts actually are, and also a bit about the history and how they are made. Those tablets are actually shown on the left, or to be more precise, it's actually a replica of such a tablet. And those historical clay tablets are actually found at several archaeological sites. For example, 22,500 of those have been found at Gültepe in Turkey. And these tablets contain various document types, such as legal documents, contracts, or private ledgers. And are also in various conditions and shapes. So some of them might be completely broken, while others are completely intact. And also the size range is completely various, so there is not a unique specialized tablet. So the catch about those is actually that the tablet, which I've shown in the earlier slide, is not actually a tablet, but rather an envelope. So such an envelope is actually pretty similar to an envelope of a letter today, in that it actually is there to protect the content or the tablet inside, and also may contain inscriptions. So we can't really destroy these tablets in order to gain access to the content on the inner tablet and in order to read those. And the material is also mostly the same. So the tablet, as well as the envelope, is actually made from silt from a riverbank, and therefore may also contain impurities like stones, for example, air bubbles, or even shells. So to scan such a tablet, a micro CT scanner is basically used to acquire a volume, three-dimensional volume of the data. And during scanning, a tablet is basically placed inside the sample holder. This sample holder is then used to capture such a projection shown here. And for that, it basically rotates the tablet or the envelope with tablet and captures such a projection from multiple angles. So coming to our task was basically, or our objective was basically to annotate such a volume with 3 different labels in order to differentiate between the tablet and the envelope itself. So for example, if I want to have the clay tablet and the clay envelope differently labeled, as well as the background, in order to remove the unnecessary information of the background. And I would hopefully get something like this, if this is done. And a further objective is that we don't want to invest manual time-consuming labeling, because those volumes get quite large, because we want a high resolution volume, because the higher the resolution, because if you imagine having like shallow letters engraved on the tablet, you might want to keep this. And you would lose those maybe if the resolution would be too low. So the resolution needs to be high enough in order to capture those. And also those should be robust to noise. And I will go into more detail a bit later about this, why. So the challenges here is then that the tablet as well as the envelope are made, because they are made from the same material, the density distribution of the tablet and the envelope is the same, and therefore it's quite hard to distinguish just by density distribution. And also they might physically touch each other inside. So the tablet might be leaning against the envelope, for example, and therefore appear as one large object in the scan. And we also have very limited amount of data available to us, because there aren't any real scan data sets or scans of those tablets. Also, because of the high resolution, we want to keep the computational cost quite low in order to reduce the computational times, because it could take quite long to scan those 22,500 tablets otherwise. And also we want to have as short CT scan times as possible in order to avoid having time requirements or adding more time. So while a nice scan would take a day or two, it's not quite feasible. So we mainly focus on the scans of 2 hours. So therefore we propose basically a pipeline that is capable of segmenting such tablets. And as our source, we use the tablet volume as the output from the CT scanner directly. And then as the first step, we basically denoise the data, then do a basic foreground and background segmentation. And with foreground background, what I basically mean is that the background is everything that does not contain information about the content on the tablet. And that could be, for example, the air that got also captured within the scanning process, or the sample holder used to hold the sample. Then as a last step, we then segment the tablet and the envelope individually and write it to, for example, on the hard drive or to a visualization software. So first of all, the denoising. The denoising really depends on the scan time, as I said before. And while it is possible to differentiate on a more abstract level, as shown here, what's the tablet, what's the envelope, it's quite hard to distinguish those at a more lower level, or if you look at a more magnified area. And there it's really quite hard to even tell what's air, what's not, or if there was a line between the tablet and the envelope. So the denoising hopefully helps a bit cleaning those up. And for that, we use a bilateral filter to denoise the volume, basically. And if we do this, it will hopefully, for example, for a sample volume, look something like this. And the nice thing actually is that the bilateral filter results in a nice distribution. For example, if this is our input distribution, where the peak is basically the background and the roll off on the right is the foreground, it results in 2 nice separate distributions, which can then be separated by using a threshold method, which we then use in our foreground and background segmentation. So for our foreground and background segmentation, we use the 2-dimensional Otsus method, which is also robust to noise, because there might be still some noise left in the, after the denoising process. So we utilize this to avoid calculating a wrong threshold. And for the final step, the tablet and envelope segmentation, we utilize the distance transform, which we calculate from the Euclidean distance. And we calculate those from each foreground voxel to the nearest background voxel. So then as our baseline, because there aren't really any state-of-the-art algorithms to my knowledge which actually do such kind of task, we use a priority plot watershed. And in particular, we use the priority plot algorithm by Wei et al., which has the advantage that it's actually optimal runtime, so to reduce our computational costs. However, as you can see, most parts of the envelope are still considered wrongly as part of the tablet, and it isn't quite feasible. therefore, we went on trying the compact watershed algorithm, which is an adaptation of the watershed algorithm and adjusts the intensity values for the watershed algorithm by the distance to the seed. And therefore, we require the user to place, for example, like 2 seeds for each part of the objects. And however, it still results in a complete planar shape and therefore doesn't capture the shape of the object. So our proposed solution is then change this metric, first of all, to account for the shape of the tablet. And for that, we require the user to place some points on the border of the tablet to the envelope to actually fit a super ellipsoid. So some points, minimum amount of points, and those points are then used to fit those super ellipsoid, and we use then the orthogonal distance of those fitted super ellipsoid as our new metric in order to find the distance from those super ellipsoid for each voxel. However, it still sometimes fails to compute the segmentation correctly, as shown here. And for those cases, we actually noted that this happens at places where the envelope and the tablet physically touch each other at bigger surface areas. And therefore, the distance transform actually results in a ridge, or what we call it connector. And therefore, the algorithm is can flow from, for example, the tablet to the envelope, and therefore results in such a wrong segmentation. What we would like to do is find those connectors that are in the distance transform and remove those by setting them to 0. So what we basically have is those distance transform here marked with the white ellipsoid. And we want to find those and remove those, and it will hopefully look something like this. And for that, we ideally want to have a function that multiplies the original distance transform with this function. And an ideal function would be, for example, setting such a ridge or bridge or connector to 0, or keep it otherwise if it's not part of such a connector. So, however, the problem here is that how do we determine what is actually a connector? And therefore, we would require kind of pre-knowledge on what is actually a connector. And therefore, we can't really use such kind of function. So as a solution to this, we noticed that actually those connectors are parallel to the normal of such a superquadratic fitted in as the approximation of our tablet. And therefore, can be used by noticing that then the gradient of the distance transform is actually orthogonal to the normals of the super ellipsoid, which allows us to use the dot product basically. And this results then in the formula here written here, where we require the user to select the factor, boosting factor, because we use a heuristic now. We don't suppress those values anymore. We boost values which aren't part of a connector, and therefore increase their value and instead of lowering the value of a connector. And therefore increase everything else and lower the values of the connector implicitly. And our results actually show that the last shown method is quite stable with on our data set, where we selected where our data set is basically the scan of one tablet with multiple subsampling factors. So we downscaled our volume by the factor of 8 and applied our methods to this smaller data set, and shown here that actually our method is quite stable, whereas the original watershed algorithm fluctuates highly with the down or subsampling factor. Also, we additionally created a perfect example or perfect labeling of those tablets and used that to apply noise afterwards in order to generate a second data set, which is then we then applied Gaussian noise to it. And we also noticed that our results are more stable than the previously shown methods. So thanks for your attention.
Okay, thank you very much for the nice talk. Very interesting work. Again, please post any questions to the Discord channel. I will start with some questions myself. Yeah, first, I was wondering that you actually do this first, basically a two-step segmentation. First, the clay versus the rest, and then you focus on the actual segmentation between the tablet and the envelope. Is this because it's much simpler? That's basically my guess. Or is because usually you can also directly try to get some multi-label segmentation.
Yeah, this is basically because it's first simpler to just remove all the noise. So our concern was that the noise afterwards, if you just directly segment the volume, that the noise might interfere with the actual segmentation if we directly segment it with, for example, the watershed algorithm. And therefore, we clean basically the data further after the denoising step using this binarization process.
I was also wondering, like, how often, like, how similar are these tablets? So you also said you're fitting a superquadratic to the shape of this tablet, as I understood correctly. Is this correct?
Yeah, that's correct. Yes.
Okay, so you essentially use this a bit like a shape prior also to get like a better segmentation. Because it was like, it reminds me a bit, the problem reminds me a bit of like a segmentation in biology, for example, for brain matter segmentation, where people, for example, explicitly use the knowledge that they know the topology, right? There's, for example, to kind of compute the surface between white and gray matter in the brain, they essentially know it's like one connected surface and there's only one piece essentially. And if these pieces, like if these tablets are not broken, then you can also try to use this information and basically looking for one closed surface. And I guess with the superquadratic fitting, that's kind of what you're doing. But there are a couple of methods in this biology research field, I guess, which might be related and could be useful for ideas.
So actually one idea was to use such a surface prior just to identify the shapes, because most of the time those tablets are actually similar in a way that they have this inside this tablet and outside, or this enclosing envelope. So there isn't really that much variation in that, but otherwise they are pretty simple, pretty similar, yeah.
Okay, now we have a question from the chat. Let me please read that. Could it help to use valley enhancing diffusion filter instead of a bilateral filter in the first stage of the pipeline? This might enhance the gap between the envelope and the tablet.
We haven't actually tested that. We just wanted, because as I mentioned earlier, we wanted to have a fast segmentation method. We just went with a GPU computed denoising method with the bilateral filter. So, but it might improve things, yes. So I haven't tested that. Might be actually worth testing this, yes.
Okay. Maybe last question about future work, like how, like what would be like the next step? So how far are we away from having like a fully automated OCR to read those clay tablets?
Actually, OCR, they're actually pretty. There are some papers about that. For example, Gilgamesh is one paper which does OCR, as I remember. So hopefully it could be directly inputted into those methods just to get then the ledger's output directly. So, but those methods are working on the tablet directly. So the problem isn't there to first separate both and then do OCR directly on them, because they already have a nice tablet to do the OCR on them.
Yes, of course, it's like a very difficult problem. Like you probably first want to flatten it and kind of get the actual inscriptions somehow in readable form rather than the shape. Okay, thank you very much. We go on with the next talk. So the next talk is from Manuel Lange, Claudio Raisch, and Andreas Schilling. It's the paper is called WLD, a wavelet and learning-based line descriptor for line feature matching, and the talk is given by Manuel Lange. Please go ahead. We cannot hear you, Manuel. Maybe you are still muted.
Okay, can you hear me now?
Yes.
And I think you have to start my video. I cannot do it. Okay, now you should see me, right?
Yes, everything is fine.
Okay, so. Good. So I'll start. Yeah, thank you for the introduction first. Yeah, our paper is about a wavelet and learning-based descriptor for line feature matching. And I'll first state our problem. So our problem is as follows. We have two images of the same scene, but from different camera perspectives. And we have them with detected lines in them. And we want to be able to match those lines. Because when we have correspondences between the lines, we can do additional things like slam or reconstruction or measuring. And we want to do the matching using a descriptor. So we chose to train a network to compute a descriptor for lines. Okay, first of all, the question, why should we use lines? If you have a point cloud like this, for example, it is hard to detect any structure or objects. But if you use lines, it's easy to quickly recognize what's going on here. So lines are well suited to represent structure, and lines do not need texture, although texture is helpful when computing a descriptor. And then if we have correspondences between lines, we can do things like localization, reconstruction, measuring, and all those tasks. So now I briefly want to say something about the uncertainty of lines versus points. Detected 2D lines have a high uncertainty along their direction, but a very low uncertainty orthogonal to their direction. This because lines consist of many points, but their endpoints can be unstable due to occlusions and the line detection process itself. For points, on the other hand, without any prior knowledge, the uncertainty is the same in each direction. Okay, and now I'll give you an overview of our approach. In the top left, you can see an original RGB image, and in the top right, you can see a grayscale image pyramid of it, both with some lines highlighted for visualization purposes. So what we do is we crop out areas around the line, we call them patches, and we crop them out from the RGB image as well as from the image pyramid, which you can see on the top right, and then in the middle right, we additionally filter those patches coming from the image pyramid with Gabor wavelets. And after that, we stack them together with the RGB patch, and this is our input to our network. Our network is then trained to compute a descriptor, and with the descriptor, we can compute the distance to other lines descriptors and see which lines are similar and match them. Okay, let's go into detail. First of all, to train our network, we needed a lot of data, and therefore we used the Unreal Engine 4. We extracted over 11 million line matches as ground truth information from 4 different seasons, which are all 4 freely available: the Epic Zen Garden, Infinity Blade Grasslands, a living room tech demo, and a sci-fi hallway. And we created a spline in each of those scenes and moved a camera along the spline stepwise. And at each step, we took an image of the current view from the camera, and we extracted the corresponding depth map of that position. Then, when we have the depth map, And the image itself, we start by detecting the 2D lines in the image, and then we project them into, we calculate their corresponding 3D lines using the information from the depth map, and then we project those 3D lines into the images of nearby camera positions, and then we check if this projected 2D line overlaps with one of those lines in the neighboring images. And if it overlaps with another line, then we know, okay, we have a match there, which we can then use as ground truth match. One problem here is that if you use just the endpoints from the detected 2D lines to calculate your 3D lines, your 3D lines can get quite skewed, as you can see in the middle image here. So this is because the 2D lines can be detected on edges of the wall or on the pole of a lamp, which is the case here. And if the line is not perfectly on the edge, but maybe the endpoint is slightly off the edge, then the depth is taken from the background and the 3D endpoint is far back in the background. So the 3D line will get quite skewed. And to avoid this, we implemented a Rensex scheme. We sampled 10 points along each 2D line and calculated their 3D positions. And then we used the Rensex scheme to calculate a proper 3D line segment out of these points, these 3D points, or reject the line at all if it was not a good line. And doing it this way, we were able to improve our ground truth matches as well as increase the amount of ground truth matches we got. Okay, let's have a look at our image pyramid. So we found out during training that a fixed line length during the training improves our results. So all patches are of the size of 100 times 27 pixels. And patches of higher levels thereby cover more of the surrounding at a lower resolution because they're from the image pyramid. And additionally, I want to mention here that lines are rotated facing upwards. We can do this because lines are detected on gradients, and gradients have a clear direction, and we can use this direction for our lines, so they also have a clear direction. So we can get invariant to rotations. Okay, now let's have a look at our Gabor convolution. One question is, why do we do this? And the answer is that we were biologically inspired here. Similar filters to the Gabor filters were found in the mammalian visual system. So we have them hardwired in our brain. Thus, we think that they are a good pre-computation step when working with features. So now that we have our patches from the image pyramid, we convolve each of those patches with two Gabor kernels. We only use two Gabor kernels to limit the amount of patches going into our network later. So you can see here, we use two orthogonal Gabor kernels, so we get two patches from each patch coming from the image pyramid. And as we got 4 patches from the image pyramid, which then results in 8 patches from the Gabor convolution, we have 8 patches from there, and we stack them with our 3 patches from our RGB image. So we have a total of 11 patches or layers, you can call them. And the whole thing, we called it our cutout stack. Then here you can see a table, and in the right column of the table, I listed the size of the receptive field of each patch. And as you can see, the RGB patches have the same receptive field as the cutout itself, so 100 times 27 pixels. And patches originating from the image pyramid have an increasing receptive field. It increases with the level they are from. Although we limited the length of the patches or the receptive field to 200 pixels because it's already far longer than most of our lines from the line detection hour. Okay, now I'll quickly show you our network architecture. It's based on ResNet, and so we start by a convolution which convolves our RGB and gamma wavelet patches. This is then followed by a max pooling layer, which is also done this way in the ResNet architecture. And then in the middle we have multiple convolutional layers, which decrease the output size from layer to layer, but they increase the depth of our tensor. And finally, in the end, we have an average pooling followed by a fully connected, which then returns our 16-byte descriptor, which can be used for matching. And I'll show you our loss function. We use the triplet loss, which is well known from the face recognition problem. It selects difficult triplets and limits the influence of already fitting triplets. Thereby it helps to avoid overfitting. It brings close embeddings, which are our descriptors in this case, together, and pushes non-matching embeddings far apart at the same time. Okay, and now let's have a look at our training. We trained multiple networks with different parameters and achieved the best results when batch normalization was turned off. The disadvantage is that with batch norm turned off, the training takes quite a while, as the convergence is quite slow, which you can see in the validation curve, which I showed here. But we achieved slightly better results than with batch normalization turned on. Yeah, so let's have a look at our results. First of all, our results, which are from scenes on the Middlebury stereo data set. I compare our method to 3 other methods, to the LLD, which is the learnable line segment descriptor for visual SLAM from Fakitov and Limpitsky, and to the DLD, which is our previous method, and to the LBD, which is the line band descriptor from Lilian Zhang and Reinhard Koch. The LBD is the only method, the only analytical method here, and also the only line descriptor so far implemented in OpenCV. It's an analytical method, and what they do is they use Gaussian bands, so they have multiple bands of different sizes along the line, so also along a region on the line, and they have multiple Gaussians which they use to convolve along the line. And so when they convolve along the line, they average the information along the line from top to bottom. So we think that a disadvantage here is that if you convolve along the line, you lose some structural information because it's all kind of smushed down along the line. And we hope that neural networks could maybe preserve some of the structural information, which was the reason why we trained our network for that. Yeah, and as you can see in the table on the bottom, on the top, we were able to do better in all the scenes. And in the bottom left, you can see some receiver operating characteristics curves, which also show that we were able to improve. And in this table, you can see also a comparison under difficult conditions in some scenes, which I took for this experiment. And we were able to do better in all except the scale change scenario, in which our previous method was slightly better. Okay, and now I can show you some result images. First, in some of the Middlebury images. So these are the first best matches for each line from the left to the right image. And all correct matches are highlighted in green, and incorrect matches are in red. And what you should see is that if there's more green, it's better. And if there are more red connections, it's worse. So in the top, you can see our method, the WLD, and in the bottom, you can currently see the DLD, which is our previous method. Or if I'll go further, you can see the result from the LPD. And yeah, we were able to score more correct matches. In the right, you can see the total number of lines. In the top, the correct number from ours, and in the bottom, the correct number from the LBD or from the DLD. Okay, now I'll go to the next scene, the bicycle scene. Yeah, it's kind of similar here. And the piano scene, where we were also able to improve the number of matches, and the vintage scene here. And let's go to our difficult condition scenes. So this is the same image, just with some blurring on it, on the right image. And yeah, we were able to do better than our previous method, or than the LBD here, on the blurring and also on the noise. And the next scenario, we took this because it has lots of repeating patterns. There are many windows, and on the border of the window can look the same on many of those windows. So we wanted to see which method can do better here, because we used a larger receptive field on our cutovers. So we thought this might be an advantage, and we were able to do better than our previous method or the LBD. And here's a viewpoint change scenario where we were also able to get more correct matches. Okay, and we also published our method on GitHub, so you can try it yourself if you're interested. Yeah, thank you for your interest, and I'm open for questions now.
Okay, thank you very much for the nice talk, Manuel. There is already one question in the chat. We're going to start with that one. So the question is, did you also try fine-tuning the Gabor kernels?
Okay, no, I didn't try that. So there's still potential to do this. Yeah, I think you could try more. You could also try more kernels in multiple directions. We just used the two in opposite directions. Yeah, but then you would have more input for the network. So it would be, yeah, something you could try out. Yeah.
Another question is, how fast is the inference of the descriptors?
Yeah, okay, so the pre-computation step takes around a millisecond per line descriptor, and the computation from the network as well about 1 millisecond. But I must say that we did not invest much time here in speeding the whole thing up. So I think there is potential to improve this. Yeah, as it can be done on a GPU and doing multiple in parallel. So I think there's potential to speed it up. Yeah.
Very nice. I also have a question myself. I was wondering, like, depending on what you get from the detector, from the line detector, how robust this descriptor is with respect to matching shorter line segments against longer ones. For example, if in one image a line is basically found entirely, and then in another image is basically split up into two line segments by the detector, how well does this then work with this descriptor? Have you seen something in the experiments?
Yeah, so the splitting up of line is one difficulty. So the thing is, as I said, we input lines with a fixed size. So if the line is smaller, we still take the size, and if the line is bigger, then also. But we do this only when training, and when using the algorithm, you can give input variable line sizes. And so I think we were able to improve this by having a larger receptive field, so looking more at the surrounding. And if the line is split up, it's still looking quite similar, depending on how long the line is and how far it is off moved away from the other line, where maybe it's one segment and in the other it's two segments. So yeah, the splitting up of lines is still a difficulty, but I think yeah, it then depends on how similar the region still is, because we are looking not only at the close area but also at the further with the patches from the image pyramid. But we have not done specific tests on that case, so I can't give you certain numbers.
Maybe one last question from my side. How robust it would be your line descriptor with respect to distortions, to image distortions? We have seen like point-based feature descriptors, which are rather robust for example, like changing the focal length. Is this something that you think will completely break or will work to a certain extent when you change the focal length? And in that respect also, can it be combined with point-based descriptors to make it even more robust, to not only rely on lines?
Okay, so the first part, I would also again say, due to our image pyramid, we are likely to be more robust to changes in the images and of the focal length. And lines also have the advantage that you can still detect them when you have, for example, some motion blur or something. If the motion is in the direction of the line, you can probably still see it very well, which is not the case for points. So I think due to the image pyramid, it is kind of robust, more robust than other approaches to such problems. And the second part, the combination with points. So I know that there are SLAM algorithms which use points and lines. So it depends how you want to combine them. But if I think you could also separately calculate a descriptor for points. But currently, I don't know if you would be able to mix them. Did you mean to mix them in one descriptor? So like have the endpoints of the line as fixed points? Or?
No more in the application that you potentially can then have like a more robust algorithm, for example, for tracking or for localization.
Oh, yeah.
There's also a follow-up question that basically asks, did you do some comparison to point-based algorithms actually?
No, so I didn't compare it to point-based algorithms, but I think there's work which has used points and lines in things like tasks like SLAM, and they showed that it's an advantage because lines are easier to detect when there are low light conditions, and also when there are not many, if there's no texture. If you only have gradients, you can still detect the lines, but it's hard to find many points. Or if you only have some structural information on houses, for example, on the edges, you can still get some structural information from lines where it's hard to detect points. So combining them is good, yeah.
Okay, I think we're out of the time schedule now. So thank you very much for this very nice talk and this work.
Yeah.
The results are quite significantly better than the previous methods. So this is quite impressive.
Thank you.
So thank you once again. And once again, I want to thank all the speakers in the session, Laura and also Tim before. So now there will be a break. So the second session of the afternoon will start at 4 o'clock. Yeah, hopefully I see many of you again. Thank you very much. Goodbye.